Bismillahirrahmanirrahim. In this video we are going to discuss that how we can linearize a non-linear mathematical equation. So consider a diode. The VI characteristics of a diode are non-linear that you can see in this graph. Here is the diode current, the forward voltage is this one. So the diode VI characteristics are like this. Okay, so this is the nonlinear equation, and how we can linearize. To linearize, first of all we will have to see the operating point. We can linearize this function in the close vicinity of our operating point. In this small section I can consider that this is the linear one. So we can linearize our function close to the operating point by assuming that the variation in this voltage and the current is very small. So delta y and delta x, this is approaching to 0, and delta y is also approaching to 0. That means that the variable along this x-axis variation, that is very small, and the variation along the y-axis, that is also very small. So with this assumption we can say that we can consider this function as a linear function in this small interval of time, or in this small range. Let's consider another function, and it is also the nonlinear function. And if we say that we are operating this system in this region where the variation in the x is from 5 to 10, and the variation in corresponding variation in the y is from, let's suppose, 7 to 12, a small range is over there in which our x and y is changing. So this is basically our operating point. So we can linearize our this nonlinear function in this region of interest, this small region of the interest. So if the deviation in the variable is very small, so then we can linearize the function, and we can then represent it using the techniques which are applicable to the linear system only. Okay, so here we have the assumption. What is the assumption? That variable deviates only slightly from some operating condition, whatever it is. If this is the operating point, then if this is the operating point, we will be assuming that the variation in x and y coordinates is very small. Similarly, over the this diode characteristics, we can say the variation in the forward voltage and the variation of the current is very small. Then we can linearize these two in the given range. Okay, so now let's consider a system whose input is x of t, right, and the output is y of t, and this function, this system is defined by this function that y is equal to f of x. And let's suppose that it's a nonlinear function, and we want to linearize it in the vicinity of our operating condition, operating points. Let's suppose that x bar and the y bar are the mean values of the range of x and y variation. What does that mean? If I look at this one, and over here I am going to say that our variable x can vary from 5 to 10. So x bar will be basically 5 plus 10 by 2, that is center point of this range, the mean value, right, x bar. Similarly, the y bar will be the average value over here. So our mean operating point is this one, mean operating point of this region. So we are going to call that operating point as x bar and the y bar. So x bar and y bar are the mean values of the range in which x and y can vary. Okay, so now considering the system y is equal to f of x, and let's expand this one with the help of the Taylor series. So we can write this function, that is y is equal to f of x, with the help of Taylor series like this, that y is equal to the f of x bar function evaluated at the operating point, then the derivative of the function with respect to the variable, and delta x. Delta x is representing the change in the variable, that is x minus x bar, right? So this one, x minus x bar. So by Taylor series, the next term will be 1 by 2 factorial double derivative of the function into the square of the variation of the variable, right? So this equation now can be written like that, because this delta x is x minus x bar, that is the deviation of the selected variable from the selected x and y. Okay, so this this equation can be written like this. As we have assumed that the deviation in the selected variables will be very small along x-axis and along y-axis, so delta x is approaching to 0 and delta y is approaching to 0, then we can linearize this function. So this x minus x bar will be very small, right? So the square will be even more smaller, so we can neglect the higher order terms, all the higher order derivatives, second derivative, third derivative, and so on. All of those can be neglected, and we can only represent our system with the help of this portion. So all derivatives are evaluated at the mean operating point, that is at x is equal to x bar, right? This derivative is evaluated at the mean point, x is equal to x bar, and we are neglecting the higher order derivatives because the change in the variable, that is x minus x bar, that is very small, right? So with this assumption we can write this equation simply like this, that y is equal to fx bar plus derivative of the function into the change of the variable. Okay, now let's suppose that this df by dx, that is the derivative of the function at selected operating point, that is x is equal to x bar is equal to k, right? So this equation can be written as y is equal to fx bar plus k into x minus x bar, and what is this fx bar? This is basically the function evaluated at the operating condition. So this will be equal to the function value at the operating point, right? So let's suppose that is equal to y bar. So this equation can be written as y is equal to y bar plus k into x minus x bar. So rearranging this equation, I can write like this. Okay, so this is the linear equation. So we have linearized our function, and that is y is equal to f of x using the Taylor series, and that is represented with this linear equation because this k is the constant one and all of these terms are the first order. So we are representing this portion of the function because we have selected the operating point, that is x bar over here, right? Basically this is the function of one variable. So for this function we can write down the linearized version with the help of this equation. Now let's consider a function which consists of two inputs, or there are two variables. So suppose y is equal to fx1 x2. It's a function of x1 and x2. So using Taylor series I can represent this one, that y is equal to function fx1 bar and x2 bar. This is the function evaluated at the operating point, right? Selected operating point, and then the from the Taylor series the derivative terms, the derivative of the function with respect to our first variable, that is x1, change in that variable x1 minus x1 bar, right? So this is the mean value of the range of the variable x1, input x1, right? Then the partial derivative of the function with respect to the second variable and the change in that variable, right, at the operating point. So these are the higher order terms from the Taylor series, right? So what we are going to do, again we are going to assume that this x1 minus x1 bar, that is very small, the variation in the variables is very small around the operating point, so we can neglect all the higher order terms which are including square or the cube or the higher one. So this will be considered 0, this will be considered 0, this will be considered 0, and we will only be left with this part of the Taylor series expansion. Okay, so from this equation I can write it like that y is equal to fx1 x2 bar plus the partial derivative of the function with respect to x1 and the change in the x1, partial derivative of the function with respect to x2 and the change in x2. Now let's assume that this is equal to k1 and this derivative of the function with respect to x2 is k2 at the selected operating point. So all of these derivatives are evaluated at the operating point at which we are linearizing our function, right? So what is this? This is a y bar, the value of the function with the operating point x1 and x2 bar. Okay, so from this equation I can write it like this, and in this equation y bar is equal to the f evaluated at x1 bar and x2 bar, and k1 is the derivative of the function with respect to x1 at the selected operating point, and the k2 is the derivative of the function with respect to the second variable x2 at the operating conditions. So from this equation I can write it like that y minus y bar is equal to k into x minus x1 bar plus k2 into x2 minus x2 bar. So this is the linear representation of this non-linear equation, non-linear function, right? That is the function of x1 and x2. Okay, so now let's look at the example that how we can use this concept to linearize the non-linear function. So let's assume that we have the function z is equal to xy and we want to linearize it in this range. The variation in the x is from 5 to 7 and the variation in the y is from 10 to 12, and in this range we want to linearize. So what is our step 1? First of all, we will have to find out the average value, average operating point, that is x bar in this range, right? So x bar will be equal to 5 plus 7 divided by 2, that is 6. So we are going to linearize it around the point where x is equal to 6 or x bar is equal to 6, and from this range if I look at the average value, that will be equal to 11, right? And with these average value, if we evaluate our function z, that is equal to xy, so that will be equal to x bar into y bar evaluated at the selected operating point, right? So operating point is that x bar and y bar, so that is equal to 6 and 11, right? So average value of the function is 66. So in the step 1 we calculate all of these average value, or we evaluate the function at the operating point and we select the operating point. If the range is given to us, the average of that range will be our operating point, right? And in the step 2 what we are going to do, we are going to evaluate the derivative of this function with respect to the variable. There are two variables x and y. So first of all, evaluating k1, that is the partial derivative of the function with respect to x at the selected operating point, right? So the function is xy, so partial derivative of xy with respect to x, that will be equal to y, and at selected point it will be y bar and that will be equal to 11, right? Because y bar is 11. Then evaluating k2 is the partial derivative of the function with respect to second variable, and that is y over here, so at the selected operating point. So simplifying that one, we are going to get k2 equal to 6. So the linearized version of this function is this one, z minus z bar, that will be equal to k1 into x minus x bar plus k2 into x minus x bar. This is our output, and these are the two variables of the function, right? So this is the linear equation. So now taking these values, z bar we evaluated over here, that is equal to 66, and x bar is 6 and y bar is 11. We have evaluated k1 over here, right, that is equal to 11, and the k2 is equal to 6. So we can write down this linear equation that will define our function, that is the product of x and y, right. So this is the linear version of that one in the selected range. And what is that range? That is basically this one, that our x is varying over here in this range and the y is varying in this range, or we have linearized our function at this operating point where x bar is equal to 6 and y bar is equal to 11. So at this operating point we have this linearized version. So now let's look at that how accurate this linearization is, so that you can consider the step 4. So let's check it at x is equal to 5 and y is equal to 10, right. So z is equal to xy, that is our exact function. So if I use the value of x and y, so x and y 5 and that will be 50. So that is the exact evaluation of the function at this point where x is equal to 5 and y is equal to 10. Now let's take this linearized equation in the proximity of the selected point. So z is equal to 11x plus 6y minus 66. So now if I take the same values of x and y over here, so I can at 11 into 5 plus 6 into 10 minus 66, so that is equal to 49. So this is the linear approximation. So exact is 50, and by linear approximation we are getting 49. So the difference is 1. So if we represent in terms of percentage error, so there is a 2% error in this linear approximation, right. So if the variation in the x is and y is small, then this is you can say a negligible difference with respect to the exact. So we can linearize the function and we can represent it with the help of this linear equation. Okay, now let's take another example. Z is equal to x square plus 4xy plus y square. This is our nonlinear function and we want to linearize it in this range. X is varying from 8 to 10 and the y is varying from 2 to 4. So first of all, calculating x bar and the y bar and the z bar, right. X bar is the average of this range, 8 plus 10 by 2 9. So we will be linearizing our function at x bar equal to 9, where x bar is representing the operating point, and the y bar is equal to 3, right. So now evaluating our function with the selected operating point. So this will be equal to x bar square plus 4 x bar y bar plus y bar square. So now evaluating it, so you will get 243. Okay, so in the step 1 we have calculated x bar, y bar and the z bar. Now we are going to find out the derivative of the function with respect to x and y at this selected operating point. And the operating point is that x bar is equal to 9 and the y bar is equal to 3. So now let's evaluate k1. K1 is given by this one, the derivative of the function, that is z with respect to x, right. So function is this one, x square plus 4xy plus y square, taking the derivative at this operating point, and that is equal to 2x bar plus 4y bar. Taking the values of x bar and y bar, we will get equal to 30. So k1 is equal to 30. Now calculating k2. K2 is the partial derivative of the function with respect to y. So evaluating this derivative, so you will get k2 is equal to 72. Then in the third step, we can write down it in the form of linear equation. So taking this expansion from the Taylor series, that is z minus z bar, that is equal to k1 into x minus x bar plus k2 into y minus y bar. So this is the operating point, right. So we have all these values, so plugging those values we are going to get this linear equation of the system that is defined by this nonlinear equation, right. So we have linearized it in this given range. Okay, then the next example for this one, let's consider that our function is y is equal to 0.2 into x3 and we want to linearize it at point x is equal to 2. So that's the mean value as well, x bar is equal to 2. So step 1 we will be calculating the x bar, so that is given 2. Now the y bar will be equal to 0.2 into x bar cube. So just using the value of x bar, so this comes out to be 1.6. So at the operating point our function is 1.6. Now in the second step, taking finding out the k, which is the derivative of the function with respect to x. So this is the derivative. So derivative of this function with respect to x, so at the operating point, that is x at x is equal to 2. So evaluating this one, so finally we will get k equal to 2.4, right. So now in the third step, writing it in the linear equation form, so y minus y bar, that will be equal to k into x minus x bar. So our output variable is y minus y bar, and this one is x. So x minus x bar, and this k is the derivative of the function with respect to x at the given operating point. So plugging in the values, y bar is 1.6, k is 2.4, and x bar is 2. So this is the equation defining this nonlinear function at the selected operating point where x is equal to 2. So in the closed vicinity when of the 2, this linearization will be valid. Okay, and the last example, let's suppose that this is the function, this range is given to us, and what we are going to do, we in the step 1 we are calculating x bar, y bar and z bar. Then we are going to calculate k1 at the operating point, that is the derivative of the function with respect to x. Then we will calculate k2, that is the derivative of the function with respect to second variable y at given operating points. And then we will use the Taylor series expansion to represent this nonlinear equation in terms of the linear equation, right. So plugging in the values, you will get the linear version of this nonlinear equation. So if I conclude, what we have done, we have learned that how we can linearize a nonlinear function at the selected operating point, right, or in the small range of the variation of the variable on which your function depends. That's all from this video. Thank you very much.